Hello, today I'm going to discuss my research which I conducted during my master MSc Physics in Government College Lahore during 87-88, and it was published in Physics Stat Solution A in 1989. So research was in 87-88, and after 1 year it was published uh, in a journal. So, and the topic was short range order in copper manganese alloy single crystals. Uh, and before this one, I will explain this one. The stress is a force per unit area, and shear stress, which is depend upon the thermal and mechanical forces. And shear stress is this is A. This is a continuous line, which is a sheet of crystals, which is A. And if you move this edge, and so that this edge will remain the same, so this shift from A to B is coplanar with the material cross section. This stress is shear stress. And if the shear stress is uh, shear stress is higher than the threshold of movement of dislocation. So movement of dislocation is higher than the movement of dislocation, then it is linked to the critical resolve shear stress in certain direction. And the solid solution hardening is the increase the strength of the solid, liquid solid, uh, by adding soluble atoms. So this is solid solution hardening, and the goal is to make highly mechanically strong alloys. So in this case, the problem which I will discuss this one, and another one is CRSS. This minimum shear stress required to move the dislocation in certain direction and certain conditions. So this is CRSS. So the introduction is that the critical resolve shear stress CRSS, which is represented by tau, and its unit is megapascal. Actually, this depends upon temperature. So according to the theory, which we will discuss, this kink pair model. So this CRSS, which is represented as a tau, is sensitive to the mode distribution of solute atoms. So this depends upon the solute atoms as and also on temperature. In copper manganese is a copper. So this also contain the but this contain some anomalous region where this theory does not fit with this one. And if we have experimental data from 4K to 300K, we will see that at the lower edge of the temperature, this theory does not work. So this is a kink pair formation model. This theory does not work. So this is, we call it anomalous region. And the stress depend upon, so what this one, that if this is anomalous behavior, so that stress depend upon the mode distribution of uh, mode distribution in copper manganese. This was the over previous research. So stress depend upon the mode distribution of copper manganese alloys. So how is in the copper manganese alloys where the shear stress does it depend upon these this one? So for this one, we will go to the formation of kink pair model. So kink pair model is explained there like this one. This is the carpet. This is the kink. This is the kink. You have activation energy to bring them closer. When you bring closer, this will have a one bigger kink like a waves. So amplitude is added by like interference. So originally, this kink pair model is for the concentrated alloys where is a short range order, but it is also good for the dilute alloys where the concentration is low. So CRSS, critical resolve shear stress, So it is more than the energy of movement of the dislocation. So it is sensitive. It is depend upon temperature, but it is sensitive to the mode distribution of solute atom. So we have to know the concentration of solute atom. So anomalous behavior is observed at the low temperature below 50 Kelvin. So stress depend upon the behavior, stress temperature behavior experimental was done, and king pair model was used to explain this anomaly. Less content than this one is a random distribution, otherwise is a regular distribution. So the copper manganese alloy is a face centered cubical crystal up to 8.3% atomic percent of solute. Objective is of this work is to find the nature of the solute of manganese distribution in copper manganese alloy using king pair model of solid solution hardening. The king pair model stress assisted thermally activated edge dislocation is edge dislocation which depend upon thermal heating, and also this is a kind of a stress. So critical results stress tau depend upon temperature, the solute temperature and the solute concentration C as this one. This is a tau is equal to tau naught. That is a stress at 0 Kelvin exponential minus mkt over w. This is not w naught. W naught. Okay. M is a mass, K is a Boltzmann constant, T is a temperature in Kelvin, W is a work, and this W depend upon N and the mean binding energy and the concentration, and GB and other parameters. So if we have experimental data of copper manganese alloy for various temperature, for various concentration of Mn, atomic percentage. So we will have this stress, which is kind of regularly linear uh, uh, behavior, except at the lower end of the temperature from 4K to 70K. You will see that instead of going in a regular way, it goes like this one. So it's the deviation from the king pair model. So fig 1, which is log linear graph of concentration of zero point 0.1 to 0.76 atomic percentage of solute of Mn. The temperature versus stress. The rate is 1.3 in 10 power minus 5 in tension at the it's a constant. So rate is a constant. So this one, if you have this equation, if you take the derivative d tau over dt, uh, rate of with respect to the temperature T, so this will go, and this is the slope. The slope is a straight line drawn through the data point. So this is the straight line, except the anomalous region, which is the 30 to 75 Kelvin, due to the enhancement of the local stress as a barrier. So enhancements of local stress, the barrier to movement of the dislocation at low temperature. So the there are barriers at low uh, temperature. So the barrier that means is the restriction to the movement of dislocation. So this work function is a variation with the concentration. As concentration increase, it goes to the highest value and then it goes to lowest value. So some this behavior relationship between W naught and Mn content concentration refer in figure 1. And also if you see this was the concentration versus N, which is N is explained in the king pair model, which we have explained. This one is W is dependent upon N and U and C. So also there is a deviation from the theory. So it is not as a straight line. It is a variable. So it has a maximum value at concentration 1. So relationship between N and C for the alloy referred in the figure 1 and 2. Arrow shows the critical concentration of 1 atomic percent of Mn. So spatial distribution of solute atom in copper manganese alloys crystals depend upon the W and N. Figure 2 shows the maximum of atomic percent of manganese, and also this one. So it is concentration dependent, and it is also W dependent, work dependent, and work function is depend upon the temperature. As low temperature goes, it has a higher value. So the final thing is the interatomic spacing through which the dislocation jump forward. If it is a smaller, then activation energy is also smaller because of the small distance. So if it is activation energy is smaller, then the distribution is random. Distribution is random atom. So, and if activation energy is larger than the activation energy is larger than the dislocation energy, so that it will push the dislocation together. The larger the alloy will be dispersed, the solute atom will be dispersed in an ordered way, and this will be a short range order. So conclusion is less content than the critical concentration 1 atom percentage randomly dispersed dislocation, whereas the local order SRO occurs in more concentrated alloys. So low dilute alloys, large long range order. For high concentration is short range order because have a high activation energy. This has a low activation energy. So if I explain to this one, is flow diagram. So CRSS, so critical resolve shear stress, which is a stress in a one direction, in certain direction, in certain condition, is usually depend upon temperature, is sensitive to the mode distribution in solute atom, and anomalous behavior is observed at low temperature between 30 to 75 Kelvin, and uh, in this anomalous behavior in stress temperature behavior, which was experimental work done, and it has been we used to explain the king pair model to explain this anomalous behavior. The less content than 1% random distribution, and higher concentration, it is short range, and there is a regular distribution. So this is the uh, research uh, in solid solution hardening, in solid solution hardening, in solid state, in solid state.